Much to the chagrin, I am sure, of none, we have now reached the very last topic of this course. And what better way to end it than let's talking about stoichiometry. But the difference this time is we're not going to use the amount of one material to calculate the amount of a second material. We are rather going to use the amount of one material to calculate how much heat is generated in the chemical reaction. Now these are made much simpler if one understands the trick. And the trick is you write your energy term, or heat term, or enthalpy term as if it were either a reactant or a product. But how do you know which one? Well, let's consider when we would write it as a product. For example, if we have the reaction A plus B goes to C, and the question tells you that 100 kilojoules of heat was given off, this phrase certainly indicates that that's a product, that the heat is given off. If it were a reactant, it would have probably said something like added. And so here we go. And we can treat this unit, we could kind of sort of think of it as just being a symbol, kind of like we have symbols for elements. And as far as the number in front of it, we can kind of treat that like it's a coefficient. So essentially we're going to write energy in line and just treat it like it's a product, a material with a coefficient. And that's what we're going to use our calculations. In just a second, I will talk about the distinction here between writing 100. Do you write it with the negative sign or do you not write it with the negative sign? It's very important here. We have two things that we need to consider. The magnitude of energy. What do I mean by magnitude? It's 100 kilojoules. That's the magnitude. And we have the direction of flow. So in this case, the direction was given by words. 100 kilojoules was given off. But sometimes there aren't words. Rather, there's math symbols that tell you. So you have to read the question and know from that, one, what side to write the magnitude of the energy. Here, because it's on the product side, that's the same thing as the word given off. And the magnitude is 100 kilojoules. You would not write the negative here. You write only the magnitude. The negative sign is what tells you to write it on the product side. Or the word given off is what tells you to write that magnitude on the product side. Well, there's only one more possibility, of course, and that's writing the heat as a reactant. And the question might look something like this. Consider the reaction of this, wherein delta H is 100 kilojoules. What's the magnitude? 100. What's the direction? Positive. So what word would you put with that? We're doing what? We're adding. And if we're adding it, guess what it is? It's what? A reactant. We would treat it as a reactant. And so in this case, I would write my reaction A plus B goes to C, and I would write the 100 kilojoules on the reactant side. Now you can also use your sign of enthalpy here. You can see if enthalpy is positive, then you're going to write it on the reactant side. And we saw earlier, if delta H was negative, then you write it on the product side. So now that you know how to do that, let's work a problem. For every 1 mole of H2 consumed, according to the following equation, 542 kilojoules of heat is generated. So what does that say? It's generated. What is that telling us? That's the same thing as it's given off. So what do we know? We're going to write it as a product. That's our equation speak. How about if I was going to put this in math speak? What would I write? Delta H is equal to minus 542 kilojoules. See, there's equation speak. I write it as a product. There's math speak. And word speak, I use something like as generated or as given off. Okay, so I know I'm going to write this on the product side. But what's the question asking us for? How much heat? Okay, I'm probably going to use the units of kilojoule for this. How much heat? How many kilojoules? Why did I choose to use kilojoules instead of calories or just joules? Or BTUs or anything else? Well, generally speaking, if the equation is working with a certain unit, I'm going to try to stick with that same unit. That way I can eliminate the need for conversion factors. So let's look at this diagram. Let's look at this schematically like we used to. Let's extract our data. So I have 20 grams of H2. I'm going to write that above H. And where does my box go? Well, I don't know what this heat value is, so I'm going to write the box above my heat value. So where are we going to go? We're going to do something very similar to what we did before, but with a slight twist. Before, we would go from gram to moles to grams of a material, but it's a little different with energy. That's the first big exception. You're going to go from gram to mole, and you're going to go straight to your answer. It's going to be a two-step conversion. So you're going to first convert grams of H2 into moles of H2. And then you're going to make a conversion factor. And here's the key. You're going to make a conversion factor as we normally do from our standard equation. And what is our conversion factor? We could write it two ways. There's 542 kilojoules of heat given off for every 1 mole of H2 we burn. Or we could write that upside down. For every 1 mole of H2 that's burned, we get 542 kilojoules of heat. Which way am I going to use it? I'm going to actually use this conversion factor this way with the 542 on top. Why is that? Well, because I'm wanting kilojoules to show up in the numerator as my answer requires. And I'm also needing moles to go away, because moles is not in my answer. And so I'm going to make a conversion factor from these coefficients, and then I'm going to finish my problem. And I wind up with 5,420. So if I burn 20 grams of H2 in this process, I can count on getting 5,420 kilojoules of heat off. Let's look at a variation of that problem. This time, let's start with 80 grams of hydrogen fluoride, but this time we know how much heat the 80 grams of material is associated with. What we don't know is the value of heat for the standard equation. And so the question might read something like this. 1,084 kilograms of heat was observed when 80 grams of hydrogen fluoride was produced. What is the heat of the standard reaction? Note, this time I know this and I don't know this. The previous question, I knew this, but I didn't know that. So the key to working these is to realize there's your relationship between mass or amount of material and energy. And we can write a conversion factor for that. We know what? That there's 80 grams of HF for every 1,084 kilojoules of heat. Or we could write that conversion factor upside down if we need to. And now what we do is we start with our conversion factor, and we're going to use this version of it. Why? Because I need kilojoules in the numerator in my answer. And so I'm going to start out with my conversion factor with kilojoules in the top. and grams of HF in the bottom. And now I'm just going to use dimensional analysis to convert grams of HF to moles of HF. And then I know my standard equation uses 2 moles of HF. And I wind up with 542 kilojoules. And one last time, note that the units cancel out that are not in our answer, and the unit that we needed in our answer showed up, and we wind up with 542 kilojoules, which we know to be the correct answer from the previous problem. And with that, that's the last problem of this semester, of the last section of this semester, and that is the end.